We're going to finish up chapter 15 tonight. So the last little bit of chapter 15 is about dependent probabilities. If two events are dependent, we can't just multiply them to find the probability of both occurring. Because they're dependent, we have to take into account one event before we use the second event's probability. So we're going to start with drawing without replacement. Basically, this is exactly how it sounds. So like if you're drawing cards from a deck, you don't put the card back. So in assigning rooms to students living on campus at a college, there are 3 left in the Gold Hall, the best, 4 in Silver Hall, the second best, and 5 spaces available in Wood Hall, the worst. For example, suppose you get to draw first. What is the probability you get in Gold Hall? So this is the probability that you get gold. There are 12 rooms total, so it's out of 12, and there are 3 in Gold Hall, so 3 out of 12, or 1/4, which is 25%. Now, you also know that your best friend is drawing second. So what is the probability that they also end up in Gold Hall? Well, we know that you have already been in Gold Hall, so that removes one of the options. So the probability that your best friend is in gold is now the total. There's no longer 12 rooms available. There's only 11 rooms because you have now taken up one of those rooms. You've also taken up one of the gold rooms, so there's actually only 2 rooms left in Gold Hall, which would give your friend an 18.2% chance of getting in Gold Hall. Another example, what is the probability that you both luck out and get in Gold Hall? So that's the probability that you get gold and your friend gets gold. So this would be the probability of you times the probability of your friend given you. Again, we're dealing with dependent probabilities here. And according to the general multiplication rule, if you have to multiply dependent probabilities, you have to multiply by the conditional probability. So we have the probability you get in Gold Hall, and then the probability your friend does given that you did. So this would be 3 out of 12 times 2 out of 11. There were 12 total spaces, 3 for Gold Hall. Then I multiply that. I already know that you're in Gold Hall, so now there's only 11 spaces available and only 2 in Gold Hall. So then we multiply those and get 1 out of 22, or 4.5%. Tree diagrams are another display that we can use to model probabilities. Tree diagrams are used in particular for dependent probabilities, when one event is based off of another event. So tree diagrams are useful when showing sequence of events. They're helpful when we want to use the general multiplication rule. For example, for men, binge drinking is defined as having 5 or more drinks in a row. For women, having 4 or more drinks in a row is considered binge drinking. Based off of some collected data, they found out that 44% of college students engage in binge drinking, 37% drink moderately, and 19% abstain from drinking altogether. 17% of binge drinkers have been in an alcohol-related car accident, and they're talking about have caused an alcohol-related car accident. 9% of non-binge drinkers have been in an alcohol-related car accident, and if you abstain from drinking, you have not caused an alcohol-related car accident. So the way that we would diagram this out looks like this. It's called a tree diagram because it has branches. So we start with 3 branches in this case. We have binge drinking at 44%. Moderate drinking at 37%, and those that abstain at 19%. These 3 percentages should always add to 100%. So when you add going down, they should add to 100%. Then, according to this, binge drinking, 17% of binge drinkers have been in an accident. So then 83% have not. And I get the 83% because 1 minus 17 is 83. For moderate drinkers, 9% have caused an accident, which means 91% have not. And again, if you abstain from drinking, you can't cause an accident, therefore 100% have not. The way we get the binge drinking and accident, or binge drinking and no accident, or moderate and accident, moderate and none, abstain and accident, and abstain and none, is by multiplying. 0.44 times 0.17 is 0.075. 0.44 times 0.83 is 0.365. You always add going down the branches, and then each set of branches should add to 100%. But then you multiply going across the branches. Using our binge drinking, let's look at an example using the tree diagram. So the first one is that I want to know what is the probability that a randomly selected college student will be a binge drinker who has had an alcohol-related car accident. So this is the probability of being a binge drinker and in a car accident. So in this case, looking at the tree diagram, a binge drinker and accident is all of this right here. And you always multiply going across the branches, so we end up with 0.44 times 0.17, which is equal to 0.075, or 7.5%. Looking at a second example, we want to know what is the probability that a randomly selected college student will be a moderate drinker who has not been in an alcohol-related car accident. So this is the probability of a moderate drinker and not in a car accident. So this is moderate and not an accident. So this would equal 0.37 times 0.91, which is 0.337, or 33.7% of the time. Doing one last example with the tree diagram, let's find the probability that a randomly selected college student has not had an alcohol-related car accident. This is a particular situation where having a tree diagram really helps, because not having a car accident is right here, here, and here. All three of these are based off of being either a binge drinker, a moderate drinker, or abstaining from drinking altogether. So I have three different possibilities to find the probability of not being in an alcohol-related car accident. So that means that I'm going to have to use binge drinker and not being in an accident, a moderate drinker and not being in an accident, and abstaining and not being in an accident. So this is going to be the probability of not being in a car accident. So this would be equal to the probability of binge drinking and no car accident, or moderate drinking and no car accident, or abstaining and no car accident. Or means we add. So this really becomes the probability of binge drinking and no car accident plus the probability of moderate drinking and no car accident, plus the probability of abstaining and no car accident. These three probabilities we have already calculated by multiplying across the tree diagram. So again, you multiply as you go across the tree diagram. So this would then become 0.365 plus 0.337 plus 0.190, which ends up equaling 0.892, or 89.2%. So the probability that a randomly selected college student has not had an alcohol-related car accident is 89.2%. Again, this is where a tree diagram really comes in handy, because we have to multiply across, but then add the different probabilities. This is it for Chapter 15, so let's look back at what we have learned in all of Chapter 15, because there was a lot that we did in here. So, for starters, the probability rules from Chapter 14 only work in special cases, when events are disjoint or they're independent. We know the general addition rule and the general multiplication rule. These allow us to add when we don't have disjoint events, or multiply if we have dependent events. We also know about conditional probabilities, which is the probability of one given the outcome of another event. Venn diagrams, tables, and tree diagrams help organize our thinking about probability, and again, allow us to use the three rules of statistics and the three rules of probability. Make a picture, make a picture, make a picture. We also know more about independence. A sound understanding of independence is going to be important throughout the rest of this course. So then, once again, two events are independent if one event does not affect the other event. And we can prove this by finding out if the probability of the first event is equal to the probability of the first event given the second event. As long as those two probabilities are equal, then we are independent. That is it for chapter 15. Have a good night, and I will see you guys tomorrow.